Ancient temples are still standing. Modern cities have fallen. That's not luck. It's a forgotten science, a science of survival. There are 20 techniques. 20 ingenious ways our ancestors built structures that could survive the worst earthquakes. Japanese pagodas. They mastered controlled sway. How did they do that? And in the Andes, there are impossible stone puzzles. What secret is inside them? This is a legacy of resilience. It's coded into the bones of these buildings. We stopped listening to the wisdom in the stones. What does that say about us? The earth could turn violent. They knew that. It wasn't a theory, it was a memory. For people living where the plates grind together, a tremor wasn't something rare. It was a recurring part of the story. The ground under them held this deep, unpredictable energy. And over centuries they learned to listen. In ancient Crete or in the Indus Valley cities, builders weren't just putting up monuments. They were having this long, silent conversation with the planet itself. Every collapse taught them something. Every wall that stayed up was a victory. This was engineering from direct experience, repeated over and over. They watched how different soils shook. They saw which shapes fell and which ones held, and they passed that knowledge down generation to generation, refining their methods. We'd call it iterative design now. Their starting point was a simple recognition. The earth moves, so we have to build things that can move with it. That basic insight brings us to the first technique. A concept that's almost elegant, like a kind of dance. That first principle turns into something real in Japan's pagodas. You see these towers standing for 1,000 years in a place that shakes constantly. The reason isn't that they resist the quake, they join it. The whole structure is flexible by design, a wooden partner moving with the earth. At the center is a huge pillar, the Shinbashira, made from a single cypress tree. But this pillar doesn't hold the building up in the usual way. It hangs from the top, loose, like a pendulum inside a wooden cage. So when the ground moves, the outer frame sways one direction, and this heavy central pillar swings the other. They counterbalance each other, absorbing that violent energy. The building sways, but it's a slow, rhythmic motion. It bends so it won't break, and that movement comes from the joinery. The beams are connected with hundreds of complex, interlocking joints, carved with perfect precision. No nails. These joints aren't rigid. They're meant to slide, to pivot, to flex. They create friction, turning the quake's energy into heat and motion that spreads through the frame. It's a shock absorber made of wood. The Horyu-ji Temple Pagoda from the 7th century proves it. It survived quakes that destroyed modern concrete right next to it. Those builders understood. Fighting nature with brute force doesn't work. You have to work with it. Let the force flow through in a way that leaves the structure intact. That ancient idea of flexible framing, of letting a building sway, it's the same principle in today's skyscrapers with their tuned mass dampers. But then there's the ground itself, what a building stands on. Our ancestors had a brilliant answer for that too, starting with a foundation that doesn't seem to make sense. Ancient builders in Mesopotamia and Greece, they faced this problem. A foundation that moves, it sounds like a contradiction. How do you build something stable on a surface that's meant to shift? Their answer was to dig down. They prepared a bed not of solid rock, but of loose material, sand, gravel, crushed seashells. Then they laid their massive stone blocks right on top of that unstable layer. To us, that looks like a mistake. It looks like the building should sink or tilt. But when the earth shakes, that granular layer becomes a protector. The individual particles, the sand and gravel, they slide against each other. They compact, they shift, and in doing that, they absorb the violent energy of the tremor. They turn it into friction, harmless friction. The energy is dispersed, it's dampened. It never travels up into the walls. It's a primitive form of what we now call base isolation. The ground moves independently of the building. The structure floats. It's isolated on a cushion of earth from the worst of the shaking. This shows an empirical understanding. They observed that rigid connections transmit force. Flexible ones can dissipate it. They turned the weakness of unstable ground into a strategic defense. So you have this clever, moving foundation, but then you place enormous, multi-ton stones on top. That creates a new problem. How do you keep those heavy blocks from cracking apart when the foundation itself is designed to move? The solution wasn't mortar, it was the deliberate absence of mortar. The third technique is architectural magic. It's in the high Andes of Peru, at the Sacsayhuaman fortress. The walls there aren't built, they're woven, enormous stones, some over 100 tons. They're carved into these irregular, polygonal shapes. Each one is a unique piece. A three-dimensional puzzle. Their edges aren't straight, they curve. They have angles with more than 4 sides, and they fit together perfectly. Even now, after centuries, you can't slip a piece of paper between them. No cement holds them, just gravity and geometry. That's interlocking polygonal masonry, and its purpose only shows when the earth moves. In an earthquake, a rigid, rectangular wall wants to crack. It cracks along its straight mortar lines, but these walls have no straight lines. When the tremor hits, each massive block can shift, just a tiny amount. They grind, they settle, they rotate slightly against their neighbors. The energy of the quake isn't concentrated, it's redistributed. It travels through a labyrinth of joints, dissipating into countless tiny movements along those zigzagging boundaries. A crack can't propagate. There's no single path for it to follow. The entire wall network moves as one. A unified, flexible skin. It's a marriage of artistry and engineering. Complexity creates resilience. The stones themselves become a shock-absorbing system. And this idea of using material for flexibility didn't stop with stone. Our ancestors looked at the earth beneath their feet. They asked a question: what if the ground itself could be engineered to protect what stands on it? The secret was in what held the stones together. We think of ancient mortar as a kind of brittle glue, but in places like Constantinople, in the Byzantine Empire, they built it differently. They engineered their mortar to be a partner. They weren't just mixing lime and water. They were making a composite material. They'd add things, finely crushed brick dust, or volcanic ash from distant eruptions, or even organic fibers like animal hair. This wasn't random. Each additive changed the chemistry. The brick dust, rich in silica, would react with the lime over time. A process we call the pozzolanic reaction. It created a stronger, more durable binder. The volcanic ash did something similar, but the animal hair, that's the fascinating part. It provided tensile strength. Think of it like reinforcing concrete with steel rebar, but on an ancient, microscopic scale. Those tiny, flexible fibers created a network inside the mortar. A network that could stretch just a little, so when an earthquake's force moved through a wall, this special mortar could deform. It could sway and flex minutely with the stone blocks. It wouldn't just shatter, it acted as a sacrificial layer designed to absorb the stress. You might see it develop a fine, web-like pattern of cracks. A controlled failure. This was deliberate. The mortar took the damage so the expensive, difficult-to-carve stones did not, and later that cracked mortar could be patched, repaired, the wall made whole again. This shows a nuanced understanding. These builders weren't chasing perfect, unchanging rigidity. They were designing for graceful degradation. They prioritized a structure's ability to survive and be healed over its ability to just stand perfectly still. It was a philosophy of resilience, baked right into the very glue of their cities. But material science was only one part. The overall shape of a building, its silhouette against the sky, held another key to stability. The mountain shape, it's a survival technique. The fifth one, ancient builders, they looked at the oldest, most stable forms in the world, and they copied them. They built pyramids in Egypt, yes, but also in Mesopotamia. Ziggurats there like staircases rising to the heavens, and in Mesoamerica, step pyramids anchoring entire cities. That shape is a geometric shield. It starts with a base so wide and heavy, it seems rooted to the earth. Then it tapers, it grows lighter and narrower as it climbs. That dramatically lowers the building's center of gravity, like a child's toy, a weighted bottom doll that always rights itself. The pyramid does the same thing. In an earthquake, the violent lateral forces, the ones that want to push a building over, they meet this immense, sloping mass. The energy doesn't just hit a wall, it's guided. The angled sides deflect that force downward, channeling it into the massive foundation, into the earth below. It's an architectural funnel for seismic energy. The structure becomes incredibly resistant to what engineers call the overturning moment, the tipping point. A tall, straight tower has a high center of gravity. It wants to pivot at its base and fall, but a pyramid's weight is concentrated so low and spread so wide that tipping it would require an almost unimaginable force. You'd have to lift that colossal base. So these builders shaping these monuments, they weren't just creating symbols of power, they were encoding a physical law into stone. Form follows function in the most profound, literal way. They gave their most important structures the profile of a mountain, because mountains endure. But a perfect shape is only half the story. The inside of these monuments, the hidden skeleton, had to be just as clever. How do you keep all that stone from collapsing in on itself during a tremor? The answer lies in a deceptive kind of emptiness. Stone is strong, but it's brittle. The ancient builders, they knew this. They knew a wall made only of stone had a fatal flaw. It couldn't bend, it could only break, so they gave it a skeleton. In the massive walls of the Minoan palaces, like Knossos, they didn't just stack stone blocks. They built a hidden grid inside, a lattice of wooden beams laid horizontal and vertical right within the masonry, like a giant three-dimensional tic-tac-toe board encased in stone and plaster. That wooden framework, sometimes cypress, that was the sixth technique. It created a composite material centuries before the term existed. When the ground shook, the stone wanted to crack, to crumble, but the wooden lattice held it together. The wood provided what the stone lacked: tensile strength, the ability to stretch, to flex, to absorb that pulling, tearing force. So the wall could sway. It could develop a web of fine cracks, but the wooden bones inside kept the pieces from falling apart. It was ancient rebar. The energy of the quake dissipated through the flexibility of the wood, saving the rigid stone from catastrophic failure. A brilliant understanding of material science, combining two elements with opposite properties to create something greater: rigid stone for compression, flexible wood for tension. Together, a resilient hybrid. And this principle, this internal reinforcement, it leads to a paradoxical idea. Sometimes, to make a structure stronger, you have to build in a deliberate point of weakness. A building can be too strong. That was the seventh insight. In ancient Anatolia, in what's now Turkey, builders used a kind of architectural judo. They didn't try to make every part of a wall invincible. They designed specific points to be weak on purpose. A single course of smaller, softer stones, or a layer of more brittle mortar. These were the fuses. When the earth shook, the force moving through the structure would find these weak points first, the path of least resistance, and they would give way. They'd crush or crack or settle, and in doing that, they absorbed a huge amount of the seismic energy. They dissipated it in a controlled, localized failure. A planned sacrifice, like blowing a safety valve to keep a boiler from exploding. The main load-bearing walls, the ones holding the roof, were spared the full force. This required an almost prophetic understanding of how stress moves through masonry, where the pressure would concentrate, which corners would bear the most strain. These builders were mapping the invisible pathways of force, and then placing a deliberate release valve right in its way. It's a profound philosophy. It accepts that damage is inevitable in a major event, so you choose where it happens, you choose how that damage happens, you control the failure so the whole system doesn't fail. It's not poor construction, it's the pinnacle of intelligent, resilient design, a risk management strategy carved in stone. This idea of controlling forces, of guiding energy through a structure, leads to another principle. One that ties everything together, from the foundation to the roof. The eighth technique is in the pattern of the bricks. It's a rhythm, a long stone laid flat along the wall. Then a shorter stone, its end facing out, tying back into the wall's core. Stretcher, then header, continuous bonding. To us, it just looks like a wall. But to an earthquake, it's a trap, because without those headers, a thick masonry wall is a deception. It's really two thin, parallel walls, one in front of the other, held by weak mortar. When the shaking starts, those two layers can peel apart. They can separate, and once they do, the wall loses all its strength. It collapses. The header stone solves that. It's a stone pin. It goes from the outer face through the heart of the wall to the inner face. It stitches the whole thickness into one piece. So when the shear forces hit those lateral waves, the entire mass has to move as one. The facing and the backing can't act alone. They're locked. This simple pattern, perfected by the Romans, passed down through medieval masons, gave walls an internal cohesion. It turned a collection of blocks into a unified, resilient skin. It shows how resilience isn't always about grand features. Sometimes it's coded into the craft. Laying one stone after another, every header was a tiny insurance policy against the chaos to come. And this principle of tying things together, creating unity from many parts, it scales up. From the pattern of a single wall to the very corners where walls meet. The roof is the last piece, and it's the most dangerous one, because in an earthquake, a heavy roof isn't just shelter. It's a weight waiting to fall. If it's not connected to the walls, it becomes a hammer. It'll pound those walls until they collapse. So the ninth technique was about making the roof a partner. Not a threat. In Nepal and Kashmir, in the traditional architecture, they solved this. They integrated it. They didn't just set the roof on top, they wove it in. They'd extend these intricate wooden timbers from the roof structure down, and they'd weave them right into the top of the masonry walls, or they'd use a continuous wooden ring beam. A wooden belt tying all the walls together at the very top, just under the roof. This stitching, roof to wall, was critical. It meant when the shaking started, the whole building had to move as one. A single, cohesive box. The roof couldn't slide off, the walls couldn't splay out. They were locked, forced to sway together, and that distributed the forces evenly across the whole system. It's a holistic view. The building isn't a collection of parts, it's a single organism, a dynamic one. They understood the seismic force travels through everything. So they tied everything together, from the deepest foundation to the highest rafter. It was a unified whole, and this thinking, this comprehensive thinking, it didn't stop at the house. It scaled up to the layout of their streets, to the placement of their temples. The builders were thinking in systems. The wisdom of survival went beyond a single house. It shaped whole cities. That's the 10th technique, urban planning with a purpose. You can see it in the ancient cities of the Indus Valley, in a place like Mohenjo-Daro. The logic is right there in the streets. The avenues are wide. There are these large, open courtyards at the center of neighborhoods, and that wasn't just for markets or processions. It was a calculated defense. When the shaking started, these open spaces acted as shock absorbers for the whole community. They created buffer zones. So if a building collapsed, the debris would fall into the plaza, not onto the house next door. That prevented a domino effect, where one falling structure could take down an entire crowded block. Those wide streets also became clear evacuation routes, unimpeded. People could flee to safety. They wouldn't be trapped in narrow alleys choked with rubble. But the planning went deeper. These ancient city planners were geologists. They read the land. They avoided building on soil that would liquefy, soil that would turn into a quicksand like slurry during a tremor. They placed their most important structures on stable bedrock, on firm ground, using the natural topography as a shield, and that reveals a shift. Resilience wasn't just an architectural feature. It was a civic value, a societal-level commitment to collective safety. The well-being of the community was literally mapped into the grid of their streets. It shows a long-term vision that protecting the city was as important as building it, and within this carefully planned city, the design of every single building still held crucial details. One of the most important was about what wasn't there, the placement of doors and windows. A wall is only as strong as its weakest point, and the weak points are the holes. The doors and windows, builders in ancient Armenia and Iran, they knew this. So the 11th technique was about controlling these weaknesses. It was a careful process. They didn't just put a hole where it looked good. They limited them. Fewer openings meant more continuous wall, more strength, and when they did make an opening, they kept it small. A narrow window, a modest door, every gap was a place where the wall's strength was compromised, where a crack could start, but it wasn't just about size. It was about position. They almost never put a door or a window right in the corner of a building, because a corner is where stress concentrates in an earthquake. It's a focal point for all that twisting energy. Putting a weak point there would invite the whole wall to split open, so they set openings away from the corners. They left solid, robust masonry at the building's most vulnerable junctions, and then they shaped the openings. They rarely used a simple flat beam, a lintel, across the top. A flat beam under heavy load wants to bend, to snap. Instead, they built arches, or they used corbelling, where each stone steps inward until they meet at the top. These shapes channel the weight of the wall above. They send it down and around the opening. The force follows a flowing pathway, distributing itself along the curves of the arch and down into the solid wall on either side. The opening becomes framed by strength, and they reinforce these zones further with thicker stonework around the frame, or with timber lintels and posts that could flex and absorb movement. This attention to detail shows a holistic view. Every element, even the emptiness, had to be engineered. The wall wasn't just a barrier, it was a continuous load-bearing network. The goal was to guide the seismic stress like a river around a rock, to make it flow through the solid parts and avoid the fragile ones. This principle of protecting the corners, of reinforcing the junctions, leads to the next step. If the corners are so critical, how do you make them unbreakable? The corner of a building is where the earthquake forces converge. It's a point of maximum pressure. A weak corner invites the whole structure to fold. So the 12th technique was about creating an unbreakable anchor. Builders, from the Andes to the Mediterranean, they didn't use just any stones for the corners. They selected the largest blocks they had, the most perfectly shaped. Often these were L-shaped stones, a single massive block carved with two smooth faces meeting at a perfect 90-degree angle. They'd set this cornerstone first, like the keystone of a puzzle. Then they'd build the two walls out from it. This L-shaped stone locked the walls together. It prevented them from sliding apart. It created a rigid, immovable joint. The Mycenaeans did this at their great citadels like Mycenae itself. Their famous Lion Gate is framed by colossal, perfectly fitted cornerstones. The Inca, masters of polygonal masonry, they still reserved their most precise stones for the corners, their most interlocking stones for the corners of temples and palaces. Why? Because a strong corner creates a stable frame. Think of a picture frame. If the corners are tight and square, the whole structure holds its shape. If the corners are weak, the frame goes out of square. It collapses. By fortifying the corners with these monumental stones, ancient builders gave the building a resilient skeleton. The seismic energy, when it hit that reinforced junction, met a unified mass. It couldn't find a purchase. It couldn't start a crack. The force was redirected back into the body of the walls, to be dissipated through their flexible masonry. This was strategic reinforcement, investing the greatest effort at the most vulnerable point. But a strong skeleton is only part of the story. The forces that travel through that frame, they have to go somewhere. They have to be channeled safely into the earth, and that requires a foundation that understands its role. Its role is not to be rigid, but to be intelligent. A wall that leans in is trusting physics. That's the inclined wall. You see it in medieval keeps, in bell towers, in old granaries. They aren't perfectly vertical. They slope inward just a few degrees from the bottom to the top. That slight tilt is a seismic shield. It widens the wall's cross-section right at the foundation, which is the most critical point. It gives the wall a broader stance. A boxer doesn't stand with feet together. He plants them wide to lower his center of gravity and brace for impact. The inclined wall does that. It resists what engineers call the overturning moment, that force in an earthquake that tries to push the top of the wall one way while the base stays put, which would make the whole thing topple. The inward slope counters it. It uses the wall's own weight, its mass, to stabilize itself. The tremor's force meets a shape that guides the energy down into that wider, stronger base. And sometimes a wall needed extra help. That's where the buttress came in. Those massive stone ribs built against the outside. We see them on Gothic cathedrals, but they're much older. A buttress is a localized reinforcement. It's like someone bracing their shoulder against yours to keep you upright. When lateral shaking hits, the buttress acts as a prop. It takes that sideways force and channels it, redirects it on a diagonal path straight down into the ground. It turns a dangerous horizontal push into a harmless vertical load. That's basic physics translated into stone, mass and geometry working together. But what if the solution wasn't just in static shapes? What if the most brilliant defense involved parts that were designed to move? The columns of the Parthenon weren't fixed, they were poised. Each drum of marble sat in a shallow socket on the platform. No mortar, no clamps, just the weight of the column and the structure above it holding it there. That was the 14th technique. When the ground shook, these columns could do something. They could rock just a little, shift and rotate in their sockets. And that small movement saved them. As the base ground against the polished stone, it created friction, a huge amount of friction. The energy of the earthquake was converted, right there, into heat and motion. It was dissipated before it could travel up and break the marble. The column would sway, take the shock, and then settle back into place. Engineers now call that a pin-base connection. Rotation without collapse. The builders knew a rigid connection is a brittle one. A column fixed solidly to its base can't give. When a quake's force hits, it creates a shear point at that junction. The column wants to snap, but a column that can pivot, that can dance for a moment, neutralizes that shear. It turns a breaking point into a rocking chair. This idea of allowing for motion, even designing for it, is a leap. It accepts the building will move, so you design the movement, you choreograph it. And this philosophy of flexibility didn't end at the column base. It was woven into the core of a structure, into the spaces between the walls. A hollow wall isn't just an empty space. It's a wall with a secret inside, a chamber. The 15th technique really showed how to turn space into a shield. Builders back then, in the Byzantine Empire and across the Middle East, they built walls with a kind of hidden duality. They weren't single, solid masses. They were two separate walls built parallel to each other with a gap left between them. That gap, that hollow core, they'd fill it with loose rubble. Broken stone, gravel, sometimes just compacted earth. It looks like a waste of space at first, but in an earthquake, that cavity becomes something else. When the shaking starts, the two outer walls vibrate. They move just slightly out of sync with each other, and as they do, their inner faces rub against all that loose fill. The granular material shifts and grinds. The kinetic energy of the tremor, the force traveling up the wall, gets transformed. It's converted into friction, into heat and sound, into the harmless movement of all those tiny stones. The hollow core acts as a damping chamber, a built-in shock absorber, dissipating the destructive energy before it can build up enough force to crack the outer shells. And there's a second layer to this, another brilliant part. Because the two walls are independent, a crack that starts in one won't necessarily jump into the other. The integrity of the whole wall system doesn't depend on a single, monolithic piece of masonry. One layer can fail in a spot, while the other keeps bearing the load. That's redundancy engineered right into the fabric of the building. It shows an intuitive but profound grasp of vibration, of structural isolation. These builders understood that a wall needed to breathe. It needed a space where energy could go to die, and this thinking about mass and movement, it leads to a counterpoint. Sometimes the solution to instability wasn't to make things lighter or hollow. It was to make them profoundly, intentionally heavy, a heavy bell at the top of a tower. It's not just a signal, it's a counterweight. The 16th technique uses mass as a dynamic partner. Builders in ancient pagodas, in medieval bell towers, they'd put enormous objects up high. A giant bronze bell, a stone statue, a massive timber beam, they had a reason for it, a reason that shows itself when the earth moves. When the tower starts to sway in a tremor, that heavy object at the top, it lags behind. Its inertia, its desire to stay still, creates a force. It pulls against the motion of the building. It creates a counterswing. That opposing force dampens the oscillation. It shortens the swing. It calms the structure like a hand steadying a rocking cup. This is a passive tuned mass damper, engineered centuries before the term existed. The principle is the same as the massive steel pendulum in Taipei 101. That pendulum sways to offset the wind, the seismic forces on that modern skyscraper. Our ancestors understood this intuitively. They observed that a structure with a heavy top behaved differently. It was more stable, so they placed their greatest weights where they do the most good. Not just structurally, but dynamically, they were tuning their buildings like an instrument, finding a harmonic balance with the forces of nature. It was an application of dynamic equilibrium, a dance of mass and motion, and this clever use of weight, it connects to something even more fundamental, a force present in every joint, every stone, every surface that touches another. The quiet, constant power of friction. Friction was the quiet protector of the ancient world. You see these massive blocks in an Egyptian temple, or those huge platform stones at Baalbek. The question is how they were lifted, sure, but it's also how they kept them from sliding. The 17th technique is about brute physics, really. It's about perfect craftsmanship. For these megaliths, flexibility wasn't the point. They wanted immovable stability, and they got it by using friction on a huge scale. The surfaces where these giant stones met weren't just rough. They were polished, almost like a mirror. When one multi-ton block was set onto another, their perfectly flat faces touched so completely that the weight alone created a massive frictional bond. Imagine two very heavy, perfectly smooth sheets of glass pressed together by an enormous force. To slide them sideways, you'd have to overcome that colossal friction. In many earthquakes, the sideways push just wasn't strong enough to do it. The stones, locked by their own weight, would shudder, but they wouldn't shift. That was stability from sheer weight and precision, but the builders went further. They added insurance. In Greek temples like the Parthenon, they used metal clamps. Iron or bronze shaped like a dovetail or a double T. These clamps were set into matching channels carved into the faces of two marble blocks. Then they poured molten lead in to seal them. This wasn't just a connection, it was an interlock. The clamp physically stopped any lateral sliding. It turned two separate blocks into one single unit. For the stones to move, the seismic force would have to shear through solid metal. This shows a different philosophy, not flexibility but perfect, rigid unity. For structures of such immense mass, the strategy was to make them act like one solid mountain, to present a face so unified, so friction-locked and interlocked, that the earthquake's energy found no weakness. It was a declaration of permanence written in stone and metal, yet behind every polished surface, every interlocking clamp, there was something else. A guiding force that wasn't physical. It was the accumulated wisdom of generations, a living system of knowledge that told them where to put each stone long before the ground ever shook. The knowledge was as important as the stone itself. That 18th technique, it wasn't a tool, it wasn't a shape, it was a living tradition, an unwritten code passed from a master to an apprentice. A deep well of collective memory. After an earthquake, the community would come together. They'd look at what had fallen, and they'd look, more importantly, at what was still standing. They'd analyze the cracks, the angles of the collapse, and that lesson, that empirical data, was then woven back into the rules of the craft. It became a proportional system. A ritual, like selecting timber only from the north side of a mountain, where the wood grew denser, or a specific sequence for laying foundation stones during a certain moon phase, which probably correlated with drier, more stable ground. These practices were often wrapped in the language of ceremony or superstition, but they were containers for hard-won seismic wisdom. They were the quality control. The standard operating procedure for an entire civilization's building program. This oral tradition created a resilient culture of construction. It meant a master builder in the 15th century wasn't starting from scratch. He was the inheritor of 1,000 years of trial and error, of observing how the earth moved. That knowledge was the true software running on the hardware of wood and mortar. It was a sustained project, a generational project in collective safety. So then you have this pressing question. If the system was so brilliant, so effective, why did it fade? Why did we stop listening to the wisdom in the stones? The answer is in a shift, a profound shift, not in our engineering, but in our relationship. Our relationship with time and memory. We traded time for speed. That was the shift. Steel and concrete arrived, the industrial age, this promise you could build anything, anywhere, and do it fast. The logic of the assembly line entered architecture, standardized parts, uniform materials, a focus on pure compressive strength, and the old techniques, the patient ones, that needed a master's eye and a season's labor for a single wall, they seemed obsolete. They were stories, not science. Modernity chose rigid frames, reinforced concrete, believing sheer mass and material strength could defy any force. It was a declaration of independence from the old, slow ways. But the earth tests our assumptions. In the 20th century, it did so with brutal clarity. Kobe, Japan, 1995. Modern highways, engineered to modern codes, lay twisted and broken. And nearby, a centuries-old wooden temple stood. It had swayed and settled, its flexible joints absorbing the shock. Or Turkey, 1999. Entire apartment blocks of rigid concrete collapsed into piles of rubble, while Ottoman-era mosques with their timber-laced masonry survived with only cracks. These weren't anomalies, they were lessons written in dust and debris. The ancient structures that endured weren't just lucky, they were proof the old wisdom held a physics we'd forgotten. A physics of flexibility, of dissipation, of dancing with the force rather than standing rigid against it. And that sparked a quiet revolution, a collaboration across centuries. Structural engineers with supercomputers now sit down with archaeologists. They use something called finite element analysis. It's a way to create a digital twin of, say, an Inca wall or a Japanese pagoda. They can simulate an earthquake, watch in slow motion how the stress flows through each irregular stone, each wooden joint. They can quantify the friction, measure the energy dissipation, map the load paths. And what they're finding is the ancient builders' intuition was a form of advanced empirical engineering. The rocking column base, it creates a predictable, non-linear response that protects the superstructure. The loose rubble core in a wall, it acts as a granular damper. The interlocking stones, they create a redundant load path network. The old myths are being translated into the language of modern physics. And this translation is no academic exercise. It's pointing the way forward. The fusion is already here. Base isolation systems in hospitals and data centers, where a building rests on sliding bearings or rubber pads, those are the direct descendants of sand and gravel foundations. The steel frames in skyscrapers, designed to bend and yield slightly, they echo the flexible wooden skeletons of Minoan palaces, even using fiber-reinforced polymers to retrofit old masonry. That's a high-tech version of those timber lattice walls. We are, in a real sense, relearning how to listen to the stones. So the 19th technique, then, isn't ancient at all. It's this very act of rediscovery. It's the humility to look back and the ingenuity to look forward, building a new resilience on the deepest foundations of all. Fusion isn't just theory anymore, it's a blueprint. Take the seismic isolation under San Francisco International Airport's terminal. The whole building sits on hundreds of these giant laminated rubber bearings. They're modern sand cushions. When the earth moves, the bearings deform. They let the terminal slide horizontally up to 2 feet while the ground shakes underneath. The principle is the same as that ancient Mesopotamian gravel foundation, but engineered with molecular precision, or the tuned liquid column dampers in Asian skyscrapers. These are massive columns of water sloshing in precisely calculated chambers at the top of a tower. As the building sways, the water's inertia creates a counterforce, damping the motion. It's the same concept as the heavy bell in the medieval tower, translated into fluid dynamics. Even shape memory alloys being researched for building frames. They're a direct descendant of that ancient idea of controlled flexibility. These metals can undergo large deformations and then snap back to their original shape, absorbing immense energy without permanent damage. They're essentially a metallic version of the resilient timber joints in a Japanese pagoda. This isn't coincidence, it's convergence. Modern science is providing the mathematical language for what ancient intuition understood physically. The interlocking stone puzzles of the Inca are inspiring a new generation of dry-stack, modular concrete blocks for retaining walls. Blocks that can shift and settle during a tremor, then be simply realigned afterward. The research is active, it's global. In Italy, engineers are studying the rubble-filled cavity walls of Romanesque churches to improve designs for modern masonry infills. In Japan, the precise carpentry of temple joints is being analyzed with lasers and strain gauges to inform new timber high-rise connections. Each project is a conversation across centuries. It proves these ancient solutions aren't museum pieces. They're a living library of resilient design, offering elegant, often low-tech answers to some of our most high-stakes engineering problems. And as we integrate these physical lessons, a deeper cultural question emerges. What does it mean to build for the long term in a world often focused on the immediate? This final perspective goes beyond technique. It's a worldview. The way ancient builders approached earthquakes reveals a cultural philosophy, one that saw humanity not as separate from nature, but in a constant conversation with it. Their architecture accepted a basic truth: the earth isn't a static platform, it's a living, shifting thing. To build on it was to enter a dialogue of give and take. Their structures weren't declarations of conquest over the land, They were careful responses. They listened to the ground's capacity for violence, and they answered with flexibility. With forgiveness, with a designed ability to yield, that stands in contrast to a more modern impulse, the impulse to dominate, to use sheer material strength to create a perfectly rigid, unchanging environment. To force the world to be still, the ancient way wasn't about forcing, it was about flowing. It embraced impermanence in the small sense, accepting that a wall might crack, that a joint might open, to ensure permanence in the large sense. The survival of the community, the continuity of a sacred space, this philosophy wove resilience into the fabric of daily life. It wasn't a separate engineering discipline. It was part of the art, part of the ritual, part of the story a community told about its place in the world, a story that acknowledged a power far greater than their own. So when you look at a Japanese pagoda designed to sway like a tree, or an Inca wall that settles like a hillside, you're seeing more than clever physics. You're seeing humility encoded in stone. You're seeing an agreement to move with the force rather than be broken by it. That invites a deeper question for us now. Beyond technical manuals and building codes, what's our cultural relationship with risk? Do we see resilience as a checklist of features to install, or as a value to cultivate? The ancient model suggests resilience is holistic. It's in the craftsman's knowledge, the city's wide streets, the community's memory of past disasters. It's a shared project, a cultural project, and as we integrate their physical solutions into our modern world, maybe the most valuable thing we can recover is this mindset. To see ourselves not as builders on the earth, but as builders of the earth, partners in a dynamic, sometimes turbulent, but ultimately sustainable dance. That brings us to the final technique, the 20th, a principle that ties all the others together, from the foundation to the roof, from the stone to the spirit. The 20th technique is more of a philosophy. It's about resilience through dialogue. Our ancestors didn't build against the earth, they built with it. They understood that to last, a structure had to listen. It had to give a little, to sway, to settle, to absorb. The flexible timber frames in Japan, the interlocking stone in the Andes, all of it is part of the same conversation. These builders were master physicists without equations. They were material scientists without labs. They were systems thinkers long before we had the term. Their work has stood for millennia. It's a testament to a design that's sustainable, that's adaptive. It accepts impermanence to achieve longevity. Now, with all our environmental uncertainty, their wisdom offers more than historical interest. It offers a blueprint built on observation, on patient innovation, on a fundamental respect for natural forces. True resilience isn't about rigid control. It's about intelligent flexibility. It's in the joint, in the shape of a wall, in the planning of a city, in the memory of a community. So next time you see an old temple, or a medieval bridge, or a traditional house where you live, look at it differently. See it not as a relic but as a resilient partner, a partner in an ancient dialogue with the planet.